second. Show you. So it relates zeta function evaluated at point 1 over qt with zeta function at t. And the coefficient here, well, so first I have t to the power 2 minus 2g. So this means that what does it mean? It means that, so G is the genus of the curve, right? Genus of x0 is G. So in particular, it follows that this rational function has degree 2 minus 2g, right? It's a polynomial of degree 2g over quadratic polynomial. So, okay, so let's prove this. Well, so zeta function is, I will write it as sum over all line bundles. So for every line bundle, we have q to the h0 of L minus 1 over q minus 1 times t to the degree, right? This is sum. Well, zeta function is the sum over effective, is the generating function for the number of effective divisors, right? And this is the number of effective divisors equivalent to L in the class L. Okay? So, and now I want to split this in two parts. I will consider line bundles of degree less or equal than 2g minus 2. And sum over, well, all other degrees, they are greater than 2g minus 2. So if you remember the proof of rationality, so in degrees greater than L, this number depends only on the degree. So that follows from Riemann theorem. And this is a polynomial, but on the other hand, it's the most interesting. It's this finite sum is the most interesting part of zeta function. It really depends on the. So what? And now, so the observation is that well, I will be mostly interested. I will try to understand what happens to this polynomial if you make this substitution. T goes to 1 over qt, and we will see that this functional equation is a corollary of the third duality. Third duality, so we will consider the involution on the set of line bundles of degree from 0 to this number that takes L to L O times omega 1. And so by third duality, we have that H0 of L minus H0 of this guy times omega 1 is equal to 1 minus g times plus degree. Okay? So if L has degree, well, I'm not interested in line bundles of degree of negative degree, because then this number will be 0, right? So this involution acts on this set of line bundles of this degree, right? Because degree of omega 1 is 2g minus 2. And let's see what kind of, let's try to apply this involution to a typical term of this term. And we'll see what happens. So, okay. So I will compute. So I take Q to H0 of L2 times omega minus 1 over over Q minus 1. Now here I will have T to the degree of L2 tensor omega. And so after simple manipulation, you will get the following expression. So just plug this formula here. So what you'll get? It will be Q to the power g minus 1, T 2g minus 2. Then it will be, which is good. And then it will be Q minus 1, T minus 1 to the power degree of L. Degree of L. Okay, and here we'll have the following. Q H0 of L minus Q to the degree of L L minus plus 1 minus G. Okay, over Q minus 1. This is a corollary of this one. And now, let's see, is it, can I use maybe this blackboard? Is it okay? So otherwise I want to have it in the blackboard. So now let's consider the following. Oh no, that's also not very good. So what can I erase? Unfortunately, I'll have to erase this. Not have enough room. Okay, so okay. So let's now consider the following expression. I will take sum over degrees from 0 to less than g minus 1. Here I will have Q to the H0 of L minus 1 over Q minus 1 times T to the degree of L. Okay. Now I will put, so then I have the second term will be just correspond to degree equal to g minus 1. So it will be Q to the sum of over all line bundles of middle degree g minus 1, Q to the H0 of L minus 1 over Q minus 1, T to the g minus 1. And then the last term will be degree now from g minus 1 to g minus 2. And what I put here is h0 of L to this number minus q to the degree of L plus 1 minus g over q minus 1 plus times q to the degree of L. Okay. So why am I writing this? I'm writing this because if you write this, denote this polynomial by u of t, right? Then say it again. Yeah. Thank you. Of course, right. So if I denote this polynomial by u of t, then this formula here implies that this whole expression, the sum, this sum, is equal to u of t plus q to the g minus 1 t to the 2g minus 2 u of 1 over qt plus middle term. So in any case, so the middle term and also this expression is invariant, satisfies this functional equation. For any function u of t, if you take this sum, it will satisfy the functional equation. So now is it clear why? So I'm saying that this formula here implies that the first term plus the second is indeed equal to this. How you see this? Every line bundle of this degree has this form for some line bundle of degree in this range. So that's why it follows. So if you make a substitution here, t goes to 1 over qt, you see that this whole sum gets multiplied by this factor. Okay, and this is true also because just because if you make substitution here, if you replace t by 1 over qt, it gets multiplied by this number. Every term here is invariant under this transformation. So what we see here is that this sum satisfies the functional equation, and we will write zeta function as sum of this polynomial and some very simple term or certain sum of geometric progression, and we'll check directly that the rest also satisfies the functional equation. Okay, so so that's how it works. So z x0t is the sum both. And the following sum. Here I will have order of the Picard group. Or maybe just write it. It's sum over all degrees greater or equal than G. Q to the degree of L plus 1 minus G minus 1 over Q minus 1 T to the degree. Okay? So this can be computed directly, and this is peak 0 of x0 times T to the G times 1 minus T inverse times 1 minus QT inverse. Okay? And so this satisfies functional equation, and this also satisfies the same functional equation by direct computation. This rational function that's satisfied. Okay? This completes the proof. Okay, so it's a little bit messy. Well, I can't really give you. So the only geometric input here was Serre duality theorem. The rest is sort of, well, it's a direct computation. But I want to see what's to explain maybe. Let's look at the simplest possible example. Let's look at the case when genus is 2. And let's try to prove the Mativik functional equation. So I remember that last time we introduced the Mativik zeta function, and we proved with rationality. I don't think that the functional equation is known, but so I think it's a very good problem, and I think it's well. I hope I will give now an argument for the simplest simplest possible case, and we will see. It will be a way to to review this computation that we made here. So the case when G is 2 is you have fewer terms, so it's okay. So let's see. So example. Let's prove Mativik functional equation. For genus equal to. The case when genus is 1 or 0, it's too simple. That's really one. So I recall that Mativik zeta function is defined as sum over OD of, well, you take the symmetric power of x0 and you multiply it by t to the t, right? So, so what we have is that this was a corollary of the argument last time, that when d, if d is greater than 2g minus 2, which is in our case is 2, then as d of x0, its class is equal to the product, the class of the Picard variety of x0 times the class of the projective space. And this projective space, well, so what is this dimension? it's the difference between the dimension of this and this. So it's I think it's so it's this has d minus g. D minus g. Very good. Yes, yes. Or at least 0 cycle of degree 1. It's enough. All the applications. So, so this means that our material zeta function is well, well, we have 1 plus symmetric power. Well, plus simply class of x0 plus times t plus the class of the symmetric square of x0 t squared plus oh, sorry, what's this? Sorry. Okay, so let's try to, so starting with this term, the symmetric powers behave, well, in a very simple way. You just have a constant term multiplied by the class of the projective space. And this is the most interesting term. So let's still analyze what is the Abel-Jacobi map in this case. We still have Abel-Jacobi map for any d. So this is Abel-Jacobi, and this will be the peak 2 of x0, well, which is because we have a rational point or cycle of degree 1, it's just p x0, right? So what is the dimension of this guy? 2. What is the dimension of this guy? Is also 2. It's well known that this map is surjective. And moreover, it's a birational equivalence. Also, when you have a smooth variety of dimension 1, its symmetric powers are also smooth, right? Because in general, it's not true in higher dimensional case. But if you take the symmetric power of A1, you are looking at the spectrum of symmetric polynomials in d variables. And this happens to be isomorphic to the ring of polynomials in elementary functions. So, so this is smooth. This is also smooth. This is a birational equivalence. How a birational equivalence can look like? So if you have a picture like this, it means that this is obtained by iterating blow-ups at points, right? So let's compute how many points we have to blow up. So what is it, by the way? What is geometrically? So where can we have a typical fiber consists of 1 point. It means that if you take a line bundle, a generic line bundle of degree 2 on a curve of genus 2, it has only one-dimensional space of global sections, right? The projectivization of this space of global sections should be 1 point. So it means that I recall that the fibers of the Abel-Jacobi map is a projectivization of the space of global sections of the corresponding line bundle. So, but there are some line bundles of degree 2 that have more sections. In fact, it is well known that any curve of genus 2 is hyperelliptic in the sense that it admits a two-fold cover of a map of degree 2 to P1. So it means that there is a line bundle of degree 2 on this curve, which has more than one dimensional space of sections. But let's see. So let's compute how many points we have to blow up to get this. How you do this? For example, you can compute the Euler characteristic. So what is the Euler characteristic of S2 of x0? Well, if you don't really comfortable with Euler characteristic of varieties of an arbitrary field, think in this point that you work over C, and think of just usual Euler characteristic. What is the Euler characteristic of the symmetric square? How you compute it? Точно. Even in that's a very good point. So maybe I will okay. So even this is true. No, this is not true. Euler characteristic. No, you can say it in a arithmetic ring. So let's compute the Euler characteristic. So what we are going to use? We have S2 of x0, and we have x0 squared, right? This is a two-fold cover, right? But it's ramified. Where it's ramified? Exactly on the diagonal. So how you compute the Euler characteristic? If you have an unramified cover. So Euler characteristic has two basic properties. Well, it's additive. That's the most important property of the Euler characteristic. And if you have an unramified cover, then the Euler characteristic of the total space is twice the Euler characteristic of the base, right? So what is the idea? Now you take x0 here, the diagonal, and here you also have the diagonal. You first remove it, right? So what you have is, I will write down the answer. So it's 1/2 plus Euler characteristic of x0 squared, right? Euler characteristic is also multiplicative. This is the Euler characteristic of this, plus 1/2 of Euler characteristic of x0. Everyone agrees with this formula? It follows from the additivity. And from the fact that if you have unramified cover, then the Euler characteristic of the base is the product of the Euler characteristic of the Euler characteristic of the total space is the product of the Euler characteristic of the base and the degree. Lisa. Мне кажется, что да. Да. Электростатистика понимает значение в целых или рациональных числах. No, okay, so let's see. So you first remove this, then what you have is the Euler characteristic of the you will have x0 squared minus c of x0 over 2. That will give you the Euler characteristic of the complement. Now you have to add the Euler characteristic of x0. So here you have negative 1/2. You add and get plus. Okay, good. So and this is 1. So what is the Euler characteristic of Picard group, of Picard scheme? 0, because it's a group, right? So you have a non-vanishing vector field. Okay, so that means that you have precisely one vector, one line bundle of degree 2 that has more than one-dimensional space of global sections, and this implies that the class of S2 in the Grothendieck group is equal to the class of the Jacobian. Oh, sorry, of pick 0, this is another name for this is Jacobian. Let's skip this. Plus what? Exactly, right? Because when you blow up, you replace a point by P1. The difference is A1 in the Grothendieck group.
So this computation with earlier characteristic, you essentially proved that a hyperelliptic involution is unique.
Yes. I don't know. So let's see. It's canonically it is peak 2, not peak 0, right? So I don't know if any way to construct a. I mean, this is a group, but this isomorphism is not canonical. So there is no kind of. I don't know of any way to construct a point here. But yeah. So. Okay. Okay. Good. So, so what does it mean? It means that our this Mativik zeta function. I will probably raise it. So this computation again, it works for Euler characteristic. It doesn't work for the class in the Grothendieck group, because for the Grothendieck group, it's not true that if you have unramified cover, then the class of the total space divided by 2. It doesn't even doesn't make any sense to divide by 2 in the Grothendieck ring. It's just a ring. It's an abelian group. It's not a Q-vector space. So okay. Anyway, so now I will. Да. Почему? Почему, если у меня есть двулистное накрытие, то оно же... Почему отсюда следует, что тотальное пространство равно дважды классу базы? Оно локально тривиальное в классической топологии, но абсолютно не в топологии Зарисского. Никогда накрытия не бывают... Они очень редко бывают локально тривиальны в топологии Зарисского, если у вас... Это тоже можно, да. Это хорошее замечание. Возьмите эллиптическую кривую, возьмите проекцию в P1, да, двулистное накрытие P1, можно построить явный пример. Замечательно. Very good. So now what we have is that zeta function now is the following, this Mativik zeta function. Mativik x0 t is 1 plus class of x0 plus class plus plus t squared times L times t squared. Okay, that's one term. And the other term, well, it will be peak 0 of x0. Well, I take its class. All right. And I will multiply it by t squared plus class of p1 t cube plus and so plus the class of p2 p2 t cube t to the fourth and so on. Okay. So so we have this decomposition. So this is the first symmetric power. The second symmetric power is decomposed using this formula here, right? And all other symmetric powers are just the products in the Grothendieck group of the Picard, of pic 0, and the projective space. So now this guy does satisfy the functional equation. So for a quadratic polynomial, the only assertion is that this is L, right? When you substitute for t1 over LT, you indeed get the same polynomial up to factor power of t and power of L. And this sum here also satisfies the functional equation by direct computation. That corresponds precisely to the decomposition in two summands that I used in the proof of functional equation for the usual zeta function. I think so. So it's really, but still I think, you can phrase the functional equation in such a way that you don't really have to divide by L. For example, a polynomial satisfies a functional, quadratic polynomial satisfies the functional equation if this term is L, right? So you don't, better not divide by L. Okay, good. So please do their, try to prove it in general. I don't think that that's unrealistic. So now, so you'll have to understand the fibers of the Abel-Jacobi map and see some symmetry there. That's very. Now, let's prove the remaining conjecture, which is the most difficult one. So how I'm going to, what I'm going to do. So let's see where we are. So we have zeta function of my curve, and I know that has the following form. It's a so it's a rational function. Here I have 1 minus t, 1 minus qt, and the top is a product I equal 1. So I know already that it's a polynomial of degree 2g because of the functional equation, right? I know that it's the rational function has degree 2g minus 2. And I can write, I will factor this polynomial as 1 minus omega I t. And so theorem that we want to prove is that absolute values of these numbers, complex absolute values, they are all equal to q to the 1/2. So, so that means that zeros of this guy are have absolute value q to the negative 1/2. And if you remember that, if you make the substitution, if you write, if you remember that z of, if you make the substitution here, t equal to q to the negative s, this is the what's really called the zeta function. Then, so this is remark. Then theorem implies that all zeros of this zeta function are on the line real part of s is 1/2. well, that's so for usual zeta function, that's what's called the Riemann conjecture, and so this is this kind of functional analog. So now. So first of all, it's well known that Riemann conjecture is related to the kind of results like the prime number theorem on the well, number of prime numbers. There is a function pi of x whose value at point x is equal to the number of prime numbers less than x. And so there are some kind of asymptotic conjectures or formulas for this function, and the Riemann conjecture is related to this. In fact, this function analog also related to this, and that's what I'm going to use. So, okay. So first claim is that theorem holds. So this is again the third part of the third Weil conjecture. Holds if and only if the following is true: the number of points on x0 with coefficients in Qn, this number is equal to q to the n plus O of q to the n over 2 as n goes to infinity. So we have this estimate for the number of points. This type of result, that's what I referred to as kind of prime number estimates. Okay, so let's see. So proof. So in one direction. So just take. Remember that if you take d over dt of logarithmic derivative of the zeta function, then this is equal to this is generating function. This number is n. And on the other hand, so what do you get? What do you have? So let's take the logarithmic derivative of this expression, and we'll find that this is sum of the following: 1 plus q to the n minus sum over I equal to 1 to g omega I to the n. Okay, g to the n. So if you take the logarithmic derivative of this guy, you get precisely this, and this gives you a formula for the numbers, for these numbers, in terms of the roots of the zeros of the rational function. I already mentioned an interpretation for this number as the trace of the Frobenius acting on homology. So this term corresponds to zero homology, this term corresponds to the second homology, and this is, it comes with negative sign, corresponds to the first homology. So, good. Now, so this already implies the statement, the claim in one direction. If the theorem holds, then the number of points is indeed, well, it's 1 plus q to the n, so n minus 1 plus q to the n, this absolute value is less or equal than 2g times square root of q to the n. So theorem implies this. And conversely, so suppose I know the asymptotic for these numbers, and I want to show that the result about absolute values of omega I. And so it follows from the assertion follows from the lemma. Suppose I have complex numbers. Okay, lambda k in C, and suppose I know that the sum of lambda I equal 1 k is bounded. For well, n goes to infinity. Then all absolute values equal to 1. It's bound. Сейчас, простите, конечно, меньше либра. Thank you. Okay? So, good. So, now I will not prove this elementary lemma in complex numbers. It will be destructive. But this lemma implied, if you apply it in this to our problem, you will see that absolute value of omega I is less or equal than square root of q. So we have we almost got what we want. We wanted to prove that that this absolute values are equal to square root of q, and we proved that they are less. How to prove that they are equal? Что? Very good. So if you so by using functional equation, if omega is 0 of zeta function, then 1 over then q over omega is also 0. Right? And therefore, absolute value of omega all equal to q. So what we will be proving is this estimate. It will imply the asymptotic formula, but so that's equivalent to the Riemann hypothesis, right? For the curve, for a curve. So we want to estimate the number of points. This is the number of points on the projective line on P1. And what we want to show that it's not that much different from the number of points on P1. Okay? So in order to do this, the proof will use a little bit more algebraic geometry than we used so far. So we will use intersection theory on surfaces. Proof. So proving this. So we have x0, and now we have x, which is x0 fq bar, and q, and we consider y, which is x times x. So we are going to use some intersection theory on this surface, and so what is? I will summarize the results that we will use this black box. Will not explain. So we have there is a bilinear symmetric form on divisors, the intersection pairing. If you have two divisors, there is a way to associate with an integer the intersection of the two divisors. So what are the basic properties? Well, it's unique. So the basic properties, well, there are two properties. First of all, that the pairing, the intersection of two divisors depends only on the linear equivalence class of your divisor. So that means that these factors through a map from peak y tensor to peak y to z. Right? That's one. And the second property, well, it says that, so I will give a name to this. Will be dot. Oh, that's the pairing. So if, or maybe I have another room, such that if C is a smooth curve, then the intersection of C and D is the degree of the line bundle of D restricted to C. Okay, so here is the picture. So you have a smooth curve C, and you have another divisor D, and I will try to write it. Okay, something like this. So this is my C and this is my D. So, and think of this pairing here as the number of intersection points computed with multiplicities. The problem is how you assign multiplicities. Well, there are many ways of doing this, and so they're sort of one way of doing this would be just to take this line bundle of D and restrict it to C. It has and compute its degree. How can you compute its degree? So this line bundle of D has a section whose divisor is precisely D, namely 1 section, which is constant section kind of 1. So, and so that means that this restriction also comes with a section, and you compute its divisor. So explicitly what you do, you take every point, you take an equation of your D, right? It's a function that defines D, you restrict it to C, and you compute the order of its 0 on C at this point. That's what you, okay? So these two properties characterize a pairing uniquely because by Berzini theorem, every divisor on a surface is linearly equivalent to a difference of two smooth curves. So that means that this property together with this determine the pair. Okay, so let's as an example. So let's consider an example. Let's compute. So I have the inside y. I have the diagonal. This is my y. So let's compute the intersection pairing of the diagonal with itself. We have some tools. So diagonal is smooth, so we can use the second property. So this will be the degree of, I take O of delta x and restrict it to delta x. So what do you get? I think this is the tangent bundle. Sorry, this is the that's the tangent. That's the normal bundle. If you have a this is the normal bundle to the diagonal, and its restriction to the curve is the tangent bundle. So this is the degree of the tangent x, and this is what is the degree of the tangent bundle? Two g minus 2 minus 2g. Right? Cotangent bundle by Riemann formula. Degree 2g minus 2. Good. So we computed the intersection of the diagonal. Now so we need one more result about the intersection on surfaces, which is called the before I state this result, I need to introduce notation. The Neuron-Savary group of a surface is a quotient of the divisor group of y modulo divisors numerically equivalent to 0. What does it mean numerically equivalent to 0? It means that the intersection, it means that intersection of my divisor with any other divisor is 0. It's in the kernel of this intersection. А говорят, 23-го уже все? Можно без масок?
Вот если нам придет приказ, да,
Ага.
мы только будем рады, когда мы сами тоже снимем. Нас же ругают. Так что извините, масочки не снимаем.
Okay, so so that's numerically equivalent to 0. And now the theorem that we'll need, again, it's Hodge index. So by the very construction of this neuron-Severi group, we have a well-defined pairing. The intersection pairing descends to the pairing on the neuron-Severi group, right? Because what we take, we just take the quotient by the kernel of this pairing. And I use the same. So the Neurocogenic Theorem asserts that the signature of this pairing is well, one rank of neuron-Severi group. Well, it has one positive entry and all other entries are negative. So if you diagonalize this form over real numbers, it will be a diagonal matrix with one positive entry and all other entries are negative. So I will formulate it in such a way that does not use finite, that this neuron-Severi group is finitely generated. So this is a true fact, but it's even harder to prove. So here is a formulation we will need. So if H is ample, then the pairing is negatively defined definite on the orthogonal complement to this ample divisor in neuron-Severi group. I will put index Q here, which means that by definition it's the rational vector space reduced from this. Okay. Numerical equivalent, so that means that it's yes, so it's a set of all D such that for every C the intersection of D and C is 0. Okay, does it make sense? So self-intersection of any ample divisor with itself is positive, right? Because its power is very ample, so you just and very ample divisor. Well, its intersection with a very ample divisor is intersection with a hyperplane for some projective embedding. It's definitely positive. So okay, that's how we're going to use it. So what we will need is a result, a very important result on about negatively definite or positively definite quadratic forms, which is called Kashi Schwarz inequality. So if corollary, if C and D are in this orthogonal complement, then the intersection of C and D is squared is less or equal than self-intersection of C times self-intersection of D. Right? You consider combination of C plus X times D, where X is a number, write that its self-intersection is positive. Think of this as a quadratic polynomial and write the condition that the discriminant of this polynomial is negative. Okay, so so how we are going to use it? We are very close to the end. So, да. Для любой. Нет, она не совпадает. Это алгебраические циклы. Это только... да, пересечение с 1,1. Да, и там это следует из теоремы неравенств Ходжа-Римана. Вообще, как устроена форма пересечения на вторых гомологиях, да на любых гомологиях. На этот счет есть неравенство Ходжа-Римана, они влекут это. Вот. Хорошо. Okay, very good. So we are going to apply this. So what we are going to use? So we will look at the Frobenius map from FQ from the curve X to itself. So this is my X. This is X. So this map F is, well, F is defined as the Frobenius on X0. Frobenius on X0 is the identity map on the scheme, and on function it's raising to the fifth power. So I will raise it to the nth power and tensor it with the identity, right? So here Q is equal to P to the n. So if you think of X as given by, as a variety given by some equations with coefficients in this field FQ, then what the Frobenius does, well, it's a FQ bar linear map, so it takes the coordinates to qth power, right? That's what this operator does. And it's so I tensor it with identity. Well, I want it to be linear, so it must be identity on constants. That's the Frobenius map. And so what do we have? What are the properties of the Frobenius? First of all, its degree of the Frobenius is equal. What is its degree? It's equal to Q. This is a very general fact. If you have any field of transcendence degree, say D over FQ bar, and if you extract all pth roots of all elements, you get an extension of degree P to the dimension, to the transcendence degree. For the curve, the degree is Q. For surface, it will be Q squared. So another property that we will need is that the differential of the Frobenius, right, is 0. Why the differential is 0? Because the differential of this Frobenius, this small Frobenius map is 0. Well, what is the differential? You need to compute. You need to show that Frobenius acts trivially on differential forms. If you have a form f d g, it sends the Frobenius sends it to f to the fifth power d to the g to the fifth power. It's 0. So and this implies that, for example, the intersection of the graph of the Frobenius and the diagonal. So I need to explain notations. Oh, maybe. Okay. So let's see here. So let gamma f That will be a closed subscheme in Y. Be the graph of Frobenius. So you have map X, and you send it to X times X, which is Y, and it's by sending using by this formula. Okay. So the image of X is called the graph. And now, if you intersect the graph of the Frobenius and the diagonal, what you get is precisely the number of points fixed under the Frobenius. This is, and this is x0 of f cubed. That's what I'm interested in. So why is that? So you have a diagonal, and you have a graph of a map from x to x. Right? And so what happens if you intersect these two smooth curves? Well, you compute in the number of points which are fixed under Frobenius, but in principle there could be some multiplicities, like in this picture. The multiplicities may occur when this curve is tangent to the diagonal. But so let's look at this equation. It tells me that the differential of the Frobenius is 0, which means that at every point, the tangent line to this graph is horizontal. It does not have a vertical direction. You can't imagine probably other curves where every tangent line is to which every tangent line is horizontal. It's hard to imagine, but the graph of the Frobenius is an example, right? So that's why. Therefore, the intersection is actually transversal, and you just compute the number of fixed points of the Frobenius. So again, if you interpret the Frobenius as the map that takes every coordinate to the qth power, it's clear that you're precisely computing the number of solutions to your equation in FQ. That's good. Good. Конечно, строго. Просто если у вас есть две кривые, это следует формально из свойства определения индекса пересечения как степени ограничения. Okay, so now let's see where we are. So I want to estimate this number, right? And we are almost in a position to apply the Kashi-Schwarz inequality, right? So let's do some. The only problem is that I can apply Kashi-Schwarz inequality only if C and D are in their orthogonal complement. So this is what you do. You take, first of all, we need an ample divisor. So in ample divisor, I pick a point on my curve, x0, fix a point, and then I consider the following divisor. Okay, so x times x0. So this will be, right? That will be horizontal line and vertical line. And I give a name to this. Okay? So this is ample. Well, why it's simple? Because x0 is an ample divisor on a curve. So if you have you have two varieties and two line bundles on this variety, then the exterior product is ample on the product of the two varieties. X0 is, I'm not saying that's very ample. I'm not sure, I don't understand what you're saying. X0 is always an ample bundle. Okay. Now, so what I'm going to do, I want to project this. I want to apply Kashi-Schwarz inequality, but first I need to kind of project these guys to the orthogonal complement. So let's do some computation. So let's compute intersection of V1 and gamma. F. What is it? So V1 is vertical line, and I want to write it's vertical, and I want to intersect graph of the Frobenius with the vertical line. What is it? One, of course. Yeah. So this is one. So what happens if I intersect this F? So now I intersect it with the horizontal line. What is it? It's Q, because it's degree. It's kind of the number of, it's degree. Good. No, if you intersect, okay. So what else do I need? I need self-intersection of Frobenius, of the graph. How you compute self-intersection? You have a graph and you want to self-intersect it. So what I compute it by definition. I take all of this guy and I want to restrict it, right? So what you get is the degree of the pullback of the Frobenius of Tx. And this is Q times 2 minus 2G. Okay. And now, what else? I think now. No. Да, почему это степень pullback? Ну, просто я утверждаю, что если взять вот нормальное рассвоение графику, это pullback нормального рассвоения к диагонали. Нет, смотрите, вот у вас график. Значит, я могу нормальное рассвоение отождествить с просто вот такими вертикальными векторами. Да, это просто будет касательное пространство моей кривой вот в этой точке. Правильно? То есть нормальное рассвоение графику — это что? Его слой вот в точке x. Сейчас, это график, да. Значит, слой в точке x равен чему? Касательному пространству в точке f от x. Правильно? Согласны? Значит, почему это точка f от x? Потому что, ну вот она. Я отождествляю нормальное расстояние здесь. Значит, это означает, что мое нормальное расслоение, это полб касательного расслоения при f. То, что тут написано. Good. So I think maybe I will, okay, 2 more minutes I need. Okay, so now I will take, consider the graph of f minus v2 minus q v1. And I will intersect it with the diagonal minus v1, v2. So why am I doing this? Because I claim that this vector here is orthogonal to both v1 and v2, and therefore it's orthogonal to h, which is sum of v1 and v2, right? So h is, yes. So, and in particular, it's, I can apply the Kashi Schwarz inequality. So why it's orthogonal to v1? If you take the product with v1, well, so self-intersection of v1 is 0, right? So product intersection of v2 and v1 is 1, and this is also 1, so it's okay. So and for the same reason, this is orthogonal, both to v1 and v2. So this is equal to, by Kashi-Schwarz inequality, this is gamma f minus less or equal than self-intersection of gamma f minus v minus q. Sorry, v2 q v1 gamma f minus v2 minus q v1 multiplied by the self-intersection of delta x minus v1 minus v2 with itself. So, and if you plug the results of our computation here, and also you need to know the intersection with the diagonal, well, what you get is that the number of f the intersection of this guy with of this guy with the diagonal minus q plus 1, right? This q plus 1, well, you obtain q plus 1 when you intersect this and v1 and v2. Is less or equal than 2g times the square root of q. So you simply use this inequality, the result of this computation, and you take the square root of both sides. That's the end of the proof. Да, было. This will be, next time we will try to prove it for q to the n. Yes, so or just replace, yeah, q by q to the n. Ну, это неподвижные точки. Такие, если у вас есть, so the question is why the intersection of the, so you suppose you have any map from x to itself, and you take its graph, and you intersect it with the diagonal. So let's compute just set theoretically. What are the intersection points? So all you need to check is that multiplicities, all multiplicities are 1. But this follows from the fact that the tangent line, so what does it mean that the multiplicity is 1? It means that the tangent line to the graph is disjoint transversal to the tangent line to the diagonal. But the tangent line to the graph is horizontal. The tangent line to the diagonal is not. Okay.
Originally, you said that Weil invented some sort of homology theory for finite fields and Higgs. So can we actually see some homology with Irving's proportion circumvented somehow?
Well, that's a very good question, and I will address it next. So kind of give a reinterpretation of this proof, which will maybe answer your question. Yeah, that's not a. The answer is not that kind of obvious or even quick to explain. Questions? Well, if there are no questions, we'll see you next Wednesday. Thank you. Have a good weekend.